Hello students, we are continuing with the topic circles. Today we will discuss an important relation when two circles intersect in 2 points. Suppose we draw two circles. Suppose this is a circle with center A and this is another circle with center B. Both the circles can be of two different radii, and the point of intersection of these two circles is joined by a line segment, and this becomes the common chord for both the circles. We need to prove if we join the centers of these circles, the line segment lies on the perpendicular bisector of the common chord. So, for this we are given two circles with center A and B, and both the circles intersect in 2 points, and CD becomes the common chord. CD is the common chord, and AB is the line joining the centers of the circle. We need to prove that the line joining the centers of the circle lies on the perpendicular bisector of the common chord. That means we need to prove that the common chord gets bisected and the common chord intersects the line that joins the centers of circle at 90 degree. That is, we need to prove that AB is perpendicular to CD. For that, we do a little bit of construction. We join A with C and then B with C, then A with D and B with D. So, join CA, CB, AD and BD. Now, we will discuss about the reasons how we can prove that. Taking two triangles, let us take triangle ABC and ABD and find out different ways to make these two triangles congruent. Now, from triangle ABC, AC and from triangle ABD, AD both are equal. Now, why is AC equal to AD? The reason is that both are the radii of same circle, and we write that reason to the right of the brackets, radii of same circle, because we know a circle can have infinite radii and all the radii are equal. Then move to that circle. For triangle ABC, BC and for triangle ABD, BD will be equal. The reason remains the same. BC is equal to BD, radii of the same circle, the circle with center B. Same reason as above. And for both the triangles, line segment AB is common. So, write AB equal to AB, common or common side. So, the triangles are congruent. ABC is congruent to triangle ABD. All the three corresponding sides of one triangle are equal to the corresponding sides of the other triangle. The triangles are congruent by side-side-side congruency rule. When these triangles are congruent, then their any corresponding angle is equal. We can take angle BAC, this angle BAC and BAD. Both angles are equal. Right angle BAC equal to angle BAD, CP, CT, corresponding parts of congruent triangles. By parts, we mean the angles and sides of the triangle taken together. So, BAC will be equal to BAD. Now, take another two triangles. We can take triangle AMC and triangle AMD. Now, take two triangles AMC and triangle AMD, and try to find out what makes them congruent. Again, side AC will be equal to side AD. The reason is radii of same circle. Then this angle BAC can be written as angle MAC. The vertex of the angle remains the same, so there is no harm in writing MAC equal triangle MAD, which is proved above. We have already proved MAC or BAC are the same angles because they contain the same vertex with same magnitude. And then AM happens to be the common side for both the triangles. AM is the side for triangle AMC. AM is also the same side for triangle AMD. We can write AM is equal to AM common. Hence, both the triangles become congruent. This time, we have proved two sides and the including angle are equal, and this becomes congruent. We say side angle side congruency rule. When these two triangles are congruent, we can say CM is equal to MD. Again, the same reason, corresponding parts of congruent triangle. CM is equal to MD. CM is equal to MD means that chord CD gets bisected by the line segment AB that happens to be the line joining the centers of the circle. So, this way we proved one part of that question, that the line joining the centers of the circle lies on the bisector of common chord. Now, the another part we need to prove is that this CD is perpendicular to AB. Now, angle CMA is equal to angle AMD. Why? Because triangles are congruent. These are the corresponding parts of congruent triangles. The reason is CPCT. Now, when you take these two angles together, the sum of these two angles form a line, and CD is already a line. You can observe that angle CMA and angle AMD both are adjacent angles, and their sum brings a straight line that their sum is equal to 180. Such angles where the sum of these two adjacent angles becomes 180 or form a straight line, we call them linear pair of angles. So, angle CMA and angle AMD, their sum is 180, and the reason is linear pair of angles. Now, angle CMA is equal to angle AMD. So, instead of CMA, write AMD plus AMD, that is equal to 180 degree. Now, continuing with this, the sum of two same angles, AMD plus angle AMD, is 2 times angle AMD. You can write twice angle AMD is equal to 180. On transposing 2 to the right side, it becomes divided by 2, cancel 180 by 2. So, the angle AMD is equal to 90 degree. AMD is the point or the angle where the two lines intersect, and if each angle is equal to 90, that means both lines are perpendicular to each other. When two lines intersect in a point, and they form at least one angle equal to 90 or one angle as right angle, we say that these two lines intersect at 90 degree, or we can say that the two lines are perpendicular to each other. So, we can write AB is perpendicular to CD. This way, we proved the both cases. An important relation that is brought by the line joining the two centers of the circle with the common chord. And we proved that the line joining the centers of two circles where they intersect at 2 points always lies on the perpendicular bisector of the common chord. Hope that you understand that question and keep this in mind. We will discuss another important theorem related to circles. It is that equal chords are equidistant from center. Now, what does this mean? If we draw a circle with center O, and we draw any two chords in that circle. Suppose the two chords are AB and CD. We are given that both the chords are equal, and we need to prove that both the chords are equidistant or at equal distance from the center. That means the length of the distance of the chord AB is as much as the distance of the chord CD is from the center. But one condition you have to keep in mind is that chords should be equal. So, this theorem says that equal chords are equidistant from center. I can write there equal chords are equidistant from center. So, how can we prove that two chords are at the equal distance? One thing we keep in mind whenever we want to find the distance between two objects or 2 points or two lines, the minimum distance is the perpendicular distance between the two. So, whenever you want to find the distance between any two objects, you always have to find their perpendicular distance. So, for that reason, we draw a line segment perpendicular on both these chords. Suppose we draw OM perpendicular on AB and ON perpendicular on CD, and we need to prove that OM is equal to ON, which brings us to the result that equal chords are equidistant from the center. Now, how this is to be proven? We have to join O with A and then O with C. Now, we will proceed with the proof. Given that a circle with center, a circle C with center O and radius R, and we are given AB is equal to CD, and we are going to prove that both the equal chords are equidistant from center. So, it is understood that the two lines from the center should be perpendicular, and we need to prove that these perpendicular distances are equal. We need to prove OM is equal to ON. For that, we join OA and OC. Now, we need to give the proof or the reasons. Now, AB is the chord and OM is perpendicular to that chord. We learnt earlier that if a perpendicular is drawn from center of the circle to the chord, it bisects the chord. So, AM is equal to MB. In reasons we can write perpendicular from center to chord bisects the chord, that chord. If you draw a perpendicular from the center of the circle to chord, it bisects it. So, AM is equal to MB, or we can write AM is half of AB. When two things are equal to each other, then each is the half of the whole. That is from the Euclid section. Keep this result as AM half of AB. Now, again the same reason for CD also. ON is perpendicular to CD, and then we have CN is equal to DN, that perpendicular drawn from chord bisects it, and each equal chord and each equal part is the half of the whole. Then CN is half of CD. Keep this result as equation 2. Because we are given that chords are equal, that means AB is equal to CD, this is given, then half of both the equal quantities are equal, then half of AB is equal to half of CD. When wholes are equal, then halves are also equal. Now you can put the relation what we got in equation 1 and equation 2. In that equation, you can put this equation as number 3. So using first and second and third, we have half of AB is AM and half of CD is CN. So we got AM is equal to CN, and now proceed with both these triangles. Now we can take triangle OMA and triangle ONC. In triangle OMA and triangle ONC, now angle OMA is equal to angle ONC. You can observe from these two triangles we are given with this right angle because OM is perpendicular to AB. Then we have its hypotenuse, that happens to be the radius of the circle. They may be equal. And the third side happens to be AM and CN. We already proved that these both are equal. So the two triangles get congruent by which rule? So angle OMA is equal to angle ONC, each 90 degree. Then from triangle OMA, OA and ONC, OC, and OA and OC are equal. You can observe from the figure, both are the radii of same circle. The reason is radii of same circle and radius of the same circle are all equal. And then the third side is AM and CN. They are equal because we proved that earlier. So the criteria of the congruency of the triangle is complete. And which rule? This is right angle, the hypotenuse and one of the sides of the triangle are equal to each other, and this rule is Rhs Congruence Rule. When these two triangles are congruent, then their any corresponding side or angle is also equal. We can say OM is equal to ON, corresponding parts of congruent triangles. So when OM is equal to ON means that the perpendicular distance from point O, that is the center of the circle, is at the equal distance from the chord AB and the chord CD. Hence, we are able to prove that equal chords of the circle are equidistant from the center. Hope you understand this property, an important property of the circles. From this relation, we can also prove that if chords are equidistant from center, then these chords are equal. You can do it yourself exactly the same way we did this theorem. If we are given that chord AB and chord CD, they are both at the equal distance from center O, then these two chords are equal. This is the converse of that theorem. So it is given that we have chord AB and chord CD, and the distance from the center is equal, OM is equal to ON, and after that you can proceed it yourself and find out the results. Hope you can understand and do that. Let's do an example from the book. Let us take another example related to the circles. We are given that there are two circles which intersect at 2 points. This is circle 1, this is the circle 2. and suppose both the circles have one circle is having radius 5 centimeter, keep it as center A, and the radius of that circle is 5 centimeter. Then we have another circle, keep this as center B, and the radius of that circle is 3 centimeters, and the distance between both the centers happens to be 4 centimeter. It is 4 centimeters distance. Now, we join these 2 points C and D, the points of intersection. It forms a common chord. We need to find out what is the length of that common chord. Now, the point of intersection is to be taken as M. We already know. Earlier, we understood that whenever two circles intersect at 2 points, the common chord lies on the perpendicular bisector of the line joining the centers of the circle. So, we understand that both the lines intersect at right angles and the common chord gets bisected. We can say from the earlier results, CD is common chord, and AB is line joining the center of the circle. Circles. So, we take the results from the earlier example that CD is perpendicular to B and CM is equal to DM, or CM is half of CD, or you can say CD is twice CM. Keep this result as equation 1. Now, the distance between the centers is 4 centimeter. We do not know how much is the distance between the point of intersection, that is M, from any center. Let me take AM as x centimeters, then MB will be 4 minus x. So, let AM be x centimeters, because AB is 4 centimeters and MB will be AB minus AM. So, what will be MB equal to? If we take the whole line segment AB and subtract AM from it, we will get BM. So, BM will be 4 minus x centimeters. Taking right triangle AMC, in right triangle AMC, we can use Pythagoras theorem. Using Pythagoras theorem, AC square is equal to AM square plus MC square. Now, it is AC is 5 square, AM is x square, and MC square we do not know. It is 5 square is 25 minus x square is equal to MC square. Keep this result as equation 2. Now, we can take another right triangle BMC and using Pythagoras theorem, we get BC square is equal to BM square plus CM square. BC square is 3 square, BM square is 4 minus x whole square, and CM square as it is. So, the square of 3 is 9, and this becomes an 4 minus x whole square becomes an identity, an algebraic identity, a minus b whole square. It is a square, 4 square is 16, plus b square, that is x square, minus 2ab, minus 2 into 4, 8, 8 into x is minus 8x, plus cm square. Now, you can take equation 2 to equation 3. Keep this as equation 3, and using the value of second and third, we get 9 as it is, 16 x square minus 8x as it is, and instead of cm square, we substitute the value 25 minus x square. Subtracting x square minus x square cancelled, we are left with 9 equal to 16 plus 25 is 41 minus 8x, or you can write transposing 8x is 41 minus 9, that is 32. 8x is 32, which brings x equal to 4, because 32 divided by 8 is 4. So, the value of x is 4. Now, using this x is equal to 4 in equation 2, so as to get cm, for that now using x in equation 2, 25 minus x square, instead of x write 4 square is equal to mc square. 25 minus 16 is equal to mc square, or mc square is equal to 9, which brings mc equal to 3. So, when mc is equal to 3 and cd is twice cm, so therefore, cd will be equal to 2 into cm, cm is equal to 3, and the common chords length is equal to 16. Hope that you understood that question in a good way.